talk about a characterization of a very specific group of planets. I'm not going to talk about planets in the habitable zone. So 90% of you don't run away. Still interesting. This is me, Travis Barman at the University of Arizona. I just quickly want to mention some of my collaborators. I'm going to be presenting some works that they participated in. More importantly, their students. So Quinn Konopacki at UC San Diego, the entire GPI team, too many names to list. Andy Skimmer is now at UC Santa Cruz, and Jordan Stone is a Hubble Fellow at U of A. And then, of course, generous support from NASA and NSF, and lots of support over the years from NextEye. So thank you very much. Okay, so I show this slide. It's my favorite star. Does anyone know which star this is? Come on. Like, there's just like tattoo material. This is HR 8799. There's B and C, and then the other planets are buried in there. And this is a raw image. There's bad pixels, a cosmic ray. Still my favorite. But for characterization, just to emphasize some of the points that Jared and Katie have already pointed out, is that it's hard because you have all this bright starlight in the way. You can't even, you wouldn't know there's a planet there unless there's a green, without the green circle, and you can kind of see B in this simple image, but there's a speckle just streaming right across its position. So if you were to just take a traditional spectrograph, a slit, boring spectrograph, and just put a slit on top of that and try to measure the spectrum, or even do photometry, you have to be very careful. And so, a lot of people spend a considerable amount of time dealing with that. And so I'm going to work through some examples. So I'm not going to go into a lot of detail and cover all of the discoveries and all the molecules that have been found and all the different mixing ratios of different things that have been discovered and all the conclusions that have been presented in the literature. I can't do that. So I'm going to work my way in terms of resolution. I'm going to start with characterizing giant exoplanets at sort of a R of order unity down to an R of order 10 to the 4. I'll just give you a few examples. And I'll focus more on the low resolution spectroscopy and medium resolution spectroscopy, and give you some illustrations of how various things in the atmosphere of the planet dramatically affect its spectrum and the interpretation that you might make about its properties. But Kate had a nice wake you up exercise, and turn to your neighbor and ask your neighbor, what snarky comment have you heard lately about direct imaging? And she showed this nice, some of you over there may not see this, but this is just that. I didn't have time to add this to my talk, but it was mass and separation in AU. And over here are the transits, and over here, where the directly imaged dips, the directly imaged planets. And so, some of the snarky comments I hear are, oh, these aren't really planets, they're brown dwarfs. That's like a punch in the gut for someone who's searching for planets. You didn't find a planet, you found a brown dwarf. And it's, if you find brown dwarfs are super interesting, and so don't feel bad if you find one, even when you were looking for planets. The other snarky comment is, okay, well, you can't even plot these objects on this diagram because you don't know the masses. Okay, the transits, you know the masses very precisely. So what are you doing plotting these even on a mass separation diagram? Because you don't even know the separation, projected separation on the sky. You don't actually know the AU necessarily, and you don't know the masses because you have to estimate them from models and crappy ages from Eric over there. So, boy, bad news here. It's a snarky comment, kind of all over the place. But I could go on and on, but I won't. But and then someone else asked a nice question about, well, how do you, when you're characterizing the atmospheres of these things, transiting planets, and characterizing the atmospheres of these things? I'm not only talking about these. Heather's going to talk about, I think, both, but mostly on transits. I'm not sure, but you'll get a taste of both from Heather's talk. So it's very difficult to directly compare the results, but not impossible. So in the transiting planet world, you're typically looking at light that's passing through the limb. So I usually use the analogy: if you take a perfectly spherical potato and take your potato peeler and make a little ring around it, you're studying that part of the atmosphere. So for these guys, you have your round potato, and you're doing an ad hoc average from your observations of what the properties are globally. The two objects are in two totally different dynamical regimes in terms of atmospheric circulation, so that's different. The temperature structures look different. The temperature structures for hot Jupiters might look, now if this were temperature and depth, or maybe isothermal, has some maybe some temperature inversion or something like that. And the directly imaged planets are going to be looking more like this. The key point, I draw the intersection here, but they have common temperatures. These are hot. So you usually if you're going to start a project, you want to go for the easiest things. You want to characterize planets, you characterize the brightest ones. And so these are the brightest ones. So these are hot because they're being roasted by their star. These are hot because they're very young. They have comparable temperatures and overlapping effective temperatures. So surface gravity. So in a temperature surface gravity diagram, they fall in similar categories. Similar temperatures, similar pressures. So you're talking about similar molecules. So that's an overlap. The atmospheric dynamics, the convective regions are in different places because the structures are different. There's a lot of differences, but some of the physics is similar enough. Chemistry, photochemistry, vertical mixing, those sorts of things. So they're important overlaps. The other thing that we have to keep in mind that what's the point of characterizing these things versus characterizing these things? We go after the ones we can do, so that's step 0. But there's a third axis that I often like to draw, and that's time. Typically, the transits are in a single plane of all common ages. These guys push this diagram out towards you, and we're looking at objects at different ages, mostly young. We're biased towards young ages, of course, but we're at least pushing this diagram out temporarily. If you want to understand planet formation, planet evolution, and so forth, you want to understand, the evolution of human beings. You don't go digging around in the crematorium or the graveyard. That'll give you a really weird answer. You actually go back and you look at the nurseries and so forth. So that's what we're doing here. It's a little morbid, but whatever. Okay, so let me go now and start with my talk. I'm a few minutes in already. I just wanted to throw that out there. I don't have slides for that. I forgot what I was talking about. Oh yeah. So now we're going to characterize some directly imaged planets. So I'm going to try to move progressively through in spectral resolution. So go forward. This is some motivations. I just said some of these things. I don't want to dwell on it too much, but occurrence rate of massive planets of wide separations. We want to know that. We start looking out here. We bias ourselves to young ages because that makes it easier to find them. Empirical limits on the initial conditions of planet formation. This is the looking back at the nurseries to understand, what were planets like at very early ages might tell us something about the processes that led to their formation. You won't learn that from looking at these weird guys. Test model predictions for spectral evolution caused by changes in cloud dynamics, vertical mixing, global circulation. So all of this work, many of you are caring about that, that special thing at 1AU down in the Earth regime. But all of this work in the brown dwarfs down into, including the transits and the directly imaged planets, while there are very few of them, these are building the foundations of our understanding. We're fine-tuned, we're sharpening our tools, developing our ninjas, training them. You guys are in the room. So this is all very important work, and don't be in a rush to get to the finish line. There's a lot of fun to be had along the way. And so this is this area. We're going to test evolution predictions in an effective temperature log G plane, for example. Typically, where you see things discussed in that luminosity age diagram that Kate showed, and I'll show that again. But there's also the effective temperature, intrinsic effective temperature of the object, and its surface gravity is an important plane from the evolution point of view. Molecular abundances, atomic abundances, those are always fun to measure, and they tell you something about the properties of the atmosphere, things like vertical mixing, potentially photochemistry, other things of that nature, but also the bulk composition, possibly like P/O ratios, things like that. And then, can we connect those things back to planet formation? That's the big picture. We want to understand how planets got there. This is that diagram Kate showed. So I'm just, again, showing a motivation. This is luminosity, and age, and these are those cooling tracks. You know, little B's are over here, big B's are over here. So stellar companions, planetary companions, little B's, big B's. And these are 1 Jupiter mass, 2, 3, 4, 5, 6, 7, 8, and so forth. And Jupiter mass moving that way. And in this diagram, you know, let's just pretend that these are all roughly the same size. There is an evolution radius, it's not super strong. And so you could draw a cut through here in terms of, you know, for constant temperatures, for example, across here. And you can look for dividing lines of atmospheres rich in, say, CO or methane or clouds and non-equilibrium chemistry, maybe variability. You can empirically map that on this diagram and then say something about the evolution of those characteristics. Are all the variables of, you know, variable planet mass objects over here? Are they more over here? Are these methane rich or CO rich or so forth? And so we can, you know, by characterizing these planets, these are the blue objects are the sort of planetary mass companions. You can debate with your snarky friends about whether they're planets or brown dwarfs or whatever, but nevertheless, you're plotting them in this diagram, and they're telling you something about the evolution of a variety of properties and giant planet-like atmospheres. Just quickly about those initial conditions. So this is hard. Like I said, just even plotting these objects on this diagram, we have crummy ages. No, just kidding. We have good ages for a lot of them. And we have luminosities, but we have to determine their masses from cooling tracks. And so this is showing you, just zooming in this region here. This is a plot from Abby Rajan's paper in 2017, sort of focusing on 2 different types of tracks with different initial conditions. So these are different starting luminosities, and these are very different starting luminosities. There's a debate on these. Maybe you can't see them, but these are the same lines as these blue lines, and these dark lines are from Marley et al. 2012, where the initial the fraction of the energy from the core accretion process that goes into heating the planet is different than in this case. And so your starting luminosity is different. And so you'll get different masses depending on which track you use. So there's uncertainty in the masses of these objects. But if we can populate this diagram with luminosity, you know, with many objects, we might find out, okay, they're all clustering around here and not up here, or vice versa. And maybe we can say something empirically about those initial conditions. This is a very, you know, we always, you know, we argue this in grant proposals. One of our motivators for direct imaging is to establish the initial conditions without another way of determining mass. That's a very hard thing to do, right? So it's a harder problem, but I'm making it sound. And then, you know, characterizing planets, you know, we're measuring the mixing ratios of molecules that contain carbon and oxygen. Can we connect this to some other, you know, formation aspects? You know, this is a simple cartoon based on a figure by Clint Konopacki, borrowed from Bruce McIntosh. Here's a star. Here's a simple disk. The brown, red, you know, brown, and that's actually brown. Bruce is colorblind, so I'm blaming him for the 2 color traces here. Anyway, there's dust grains, CO2 ices, H2 ices scattered through here. As you move through the disk and cross different frost lines, the gas will have a different C/O ratio. And so the fraction of solid to gas that you accrete from your planet will say something about, or the C/O ratio in your atmosphere will say something about the fraction of solid to gas that you accreted and where in the disk you formed. And so we can maybe characterize the planet in terms of the abundances of these molecules and say something about planet formation. This is hard, very hard, but something to do. Okay, so now I'm going to go through a couple of examples as quickly as I can. So here, you know, I borrowed a ton of money. I gave it to Jared, and he built me a wonderful instrument for directly imaging exoplanets. And then Kate went to the telescope, observed a bunch of stars, and rejected a bunch of false positives. And we made a discovery. Here it is. And this is HD number. And I emailed Eric, what's the age of HD number? And he told me, you know, what? He told me it was 30 million years. I'm going with the 30 million years that he told me. I don't know. He changed his mind. But anyway, so here's a star, and look, there's a companion, and we've done all the stuff that Kate requires us to do to reject false positives. And so now I want to characterize it. Of course, read the fine print here. This is made up. this is yeah, it's made up. This is totally made up. This is real data. I'm making up examples using real data. It doesn't matter what the real names are. I'm respecting their privacy. But this is a background object that I discovered. You know, you probably didn't read that paper, so I didn't write it. But anyway, so there it is. This is a K-band image. And now I want to characterize this planet. The nice thing about direct imaging, as soon as you have a discovery, you immediately can start characterizing it, right? You have photons from it. There it is. I know how bright it is in the K-band. That's exciting. I'm excited. I have a star with a wide companion. There it is. And Eric told me the age. I used a bolometric correction from brown dwarfs, for example. Maybe that's just a starting place to get its luminosity. And I plotted on that nice luminosity age diagram from Brendan Bowler's paper. And there it is, the big green dot. So its luminosity relative to the sun is 10 to the minus 5. And its age was something like 30 million years. Thank you, Eric. And now I can go 1, 2, 3, 4, 5, 6. It's between 6, 7, 8, and 9. Between 6 and 9 Jupiter masses. Okay, now I can put it on here. So 7 Jupiter masses. That's great. I've already started characterizing my exoplanet. This is sort of that R of unity case where the resolution is very low. I have a photometry point. What else can I do? Well, I can take another image at a different wavelength in the J band, for example, and now I can plot it on a color magnitude diagram. So how red is it in J minus K, and how bright is it in absolute K magnitude? And I can compare it to brown dwarf, evil brown dwarf. This is the planet. Don't get confused. So here's my planet. It sits here. And so I can look at calculations of stellar atmospheres. I'm going to go into how this works. But if you were to plot stellar atmospheres of different temperatures without clouds in them, it would follow this blue line. And if you were to put a bunch of clouds in the atmosphere, they would follow this red line. If they look like black bodies, they would follow this dashed line. This is how a color magnitude diagram path of a black body would look like. And so I can go over here and go, okay, my J minus K was 2, my absolute K minus 15. It plots here. I thought it's an interesting part of the space. It's not around where brown dwarfs hang out. It's over here. And so I know that because it's red relative to a clear, it's probably got some clouds in its atmosphere. So with 2 photometric band passes, in fact, I'm able to separate the light from the planet and star. I've already done a considerable amount of characterization. It's probably got some clouds in it. About probably 7, it's certainly less than 14 Jupiter masses, unless Eric really messed up on the ages. I'm sure he didn't. It's perfect, right on. Okay, now I can keep going. I can get more. There's more filters on the filter wheel. So I can march through all the different filters on the filter wheel and take these points here. So the data are in black. I wasn't able to get a detection out here. I have an upper limit. And I can start comparing synthetic photometry to my observations. These are real observations from way back. They're not relevant anymore. They've been updated and replaced with them. Doesn't matter which object. Some of you might know where this figure came from. At this point's bad. But anyway, it's realistic, right? Some of your photometry is going to be reliable, some of it's not. So there's speckles and things of that nature. Maybe you weren't able to, maybe you didn't actually have a good magnitude for the star, which you're using to leverage the planet brightness. Anyway, so you fit, these red points are all from a single model, and I conclude that's my best one for my grid. I had a grid of synthetic photometry that depended on effective temperature and gravity. Solar abundances, very vanilla kind of thing. And so I can get an effective temperature and a gravity from that. And it's 1100 Kelvin log G of 4 is my best match. It's not a perfect match. Not a perfect match, obviously. So you have to deal with that. This is a little bit of realism coming in there. But I go over to my theoretical landscape over here. Here's effective temperature. Here's log 3. These curves are constant ages. So here's all objects of 1 mega year would fall here. 30 million years, which is where my object lies here, 500 million years. And then these are lines of constant mass, pulled from the same tracks from the luminosity age diagram. So each of those tracks of luminosity versus age, there are temperatures and gravities that go with those objects along those tracks. And so I can make the same, plot the same information here and compare my sort of atmosphere only, independent. I haven't used any other information here except just what matches my colors and photometry. And I can compare that to what the evolution models say. So at 30 million years, this little gray box here is sort of the error box of my luminosity. So in this gray zone is where all the models of the cooling tracks have the same luminosity as my object, independent of the age. So I march along here. I have some error bars on my luminosity based on my bolometric correction version, or I do a better job here now that I have more of the SED. And then if I just truncate, where the age, the error bars that Eric gave me on the ages, that if this object has properties that are consistent with the cooling track prediction for a few Jupiter mass, so 7-ish Jupiter mass object of 30 million years, that and my atmosphere models aren't complete garbage, then I should land in the same box. So this is showing an example of a consistency between my atmosphere only, my synthetic photometry comparison to my object that I'm characterizing with photometry, and the prediction for its properties based on the age and the bolometric luminosity. Once you have a lot of photometry, the bolometric luminosity is good. It's really model independent. You could say black bodies, a variety of other things. You'll still get roughly the same, within the error bars you care about. So this is just showing you a quick example of characterization, just with photometry. All right, so we want to move on. When do I end? 20 minutes. There's the timer, right? 20 minutes. So direct spectroscopy, there's too many to discuss. These are all the various instruments, some in the near future, with which you can use to directly characterize these giant directly imaged exoplanets. I'm just going to go through a few examples. Here's 51 Airy. Pete already showed this nice movie, Stepping Through in Wavelength. I don't need to describe it anymore, but you can, in the modern era, we don't just get photometry anymore, we get spectra at the same time, and so we immediately can characterize even more. We can say, look, there's methane absorption. I can compare this to T-dwarfs, for example, or models, and no, this is very, very, very well reproduced by typical methane absorption without any doubt. Here's showing a model, a more detailed model, not synthetic photometry, but a detailed model comparison to the data from Avi's paper, showing more observations than are plotted here. And you can get information about cloud metallicity, cloud properties, planet radius, the effective temperature and luminosity, you can estimate the radius. Sphere also has a nice discovery. Here it is. Here's a plot of the sphere discovery spectrum in flux and wavelength. They're highlighting potential molecules. They don't claim, I think, a detection of these in here, but water almost certainly shapes these others are possibilities for the temperature of this object, which is probably about 1700 Kelvin. And there's a nice retrieval model, I think, or forward. I can't remember if this was a retrieval from ExoReams. There's the reference to that. And so in the modern era, the point is you get direct spectroscopy and you can go further. The nice thing about having spectroscopy from a single instrument, the photometry I showed before was from a hodgepodge of telescopes. The previous one was from 4 different telescopes, 4 different groups, and they have different schemes for addressing the things that Kate mentioned. And so it's not a homogeneous data set, but this is a nice, you can trust somewhat the homogeneous nature of how the data were massaged and developed. And then you can go to higher spectral resolutions, medium resolution. So this is another integral field spectrograph from Osiris on Keck. Here's C in this box. No, B in this box here. This box sort of fits right here on the sky, and you can see the speckles streaming by. Very similar to the movie, the GPI movie. So it's stepping through in wavelength, and this is spatial position. You can take a bright speckle and look at it. It has pretty simple properties. You can model that, subtract it from this cube, and then get something that's cleaner. This is one exposure, so you would stack many of these. You can see the planet there not moving. The speckles are moving. And then you can get a spectrum. This is a real spectrum, not a model, at R of 4000. It has the right shape. You can see absorption from water. You can see individual water lines and CO and methane in the spectrum. And integral field spectrographs are pushing into the thermal infrared. So here is a new instrument or a new mode on an existing instrument at LBT called AILS, which stands for the Arizona Lenslet for Exoplanet Science. Funny name. And here are showing, rather than showing a movie, these are slices and wavelengths. You can. This is a brown dwarf binary, HD blah 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 from HP Boo, has a relatively smoothly varying spectrum. So a movie would be not as exciting as the 51 area one, but just showing you the binary here. And this is a nice paper by Zach Wiesmeister that's coming out soon as a grad student at UC Santa Cruz. And then there's just two different models fit to the observations, determining the temperatures and gravities. And ALS has looked at HR 8799, C, D, and E, so that's coming soon. So we'll get thermal IR spectra rather than photometry across this wavelength range. Actually get spectra very soon from Jordan Stone. GPI has taken lots of spectra, so has the transit community. So in the spirit of that question about how do transit spectra and direct imaging spectra compare and kinds of information we can get, here's data from David Singh's group from 0.3 to out to 4 microns. Here's the GPI gallery that Rob DeRosa put together of spectra from GPI from 1 to 2.25-ish or 2.5 microns. And they're different, totally different spectra, right? Here you can see clear molecular absorption. Down at 51 area, you can see methane absorption, water absorption, and moving up in temperature for the objects. This is 2700 Kelvin. In the transit community, there's a wide variety of objects. The spectra all look somewhat similar, but the signal to noise is generally greater in the direct imaging objects, and it's sort of a comparable number, just to show a comparison. Never enough time. So moving on, I'm going to show a couple of quick slides that illustrate the modeling. This is just my go-to diagram that shows sort of the flow. Typically, sometimes I find students and postdocs a little confused about atmosphere models and evolution models. They tend to lump together because you would sometimes go to evolution grids and get colors. And this diagram is to simply show how the flow of information and the interplay between the two things work. So atmosphere models sit over here. They provide upper boundary conditions for the evolution models. Those don't work unless you have these. And the interior models, those cooling tracks, the luminosity versus age, those typically come with colors. Those colors come from atmosphere models. Generally speaking, the results of the cooling tracks are not that sensitive as long as you have non-gray opacities in your atmosphere, the boundary conditions. Those cooling tracks are not that sensitive to those. But the predicted colors, if you were to plot isochrones or lines of constant mass in a color magnitude diagram, those are immensely sensitive to the atmosphere models that were used, whether they were cloudy or cloud-free. So there's a lot of dependence on the predictions of the interior models on the atmosphere models. And then that flows to the colors and magnitudes, which depend on age and mass when you compare to observations. The luminosity and radius, the green ones are, these are sensitive to the boundary conditions, but you can mess those up and not change the results too much. But then the atmospheres, you can go directly to comparing your observations through the spectra they produce and bypass the interior models altogether. You're not wedded to those in any way. You can, and so it's very important that this avenue is explored in addition to this one, because we want, that example I gave before is you just compare models to the photometry and don't worry about the interior. That self-consistency gives you important information about how well maybe the atmosphere models are doing and how well the interior models are doing. Brown dwarfs are important. We've learned a lot of information that helps us and guides us in our interpretation of giant planets. I list a few. The masses are overlapping, 1 to 80 Jupiter masses, similar radii, ages, millions to billions, gravities, 2 orders of magnitude. Temperatures are comparable, clouds are comparable, non-equilibrium chemistry and vertical mixing, we see those in brown dwarfs as well. Dynamics and weather, we see that in brown dwarfs as well. The main difference is formation and composition in early evolution. All right, so I have about 10 minutes. I'm going to go through, I'm going to not make it all the way to R of 10,000, I don't think. So here's my sketch of what I'm, if you wanted to cook up a model atmosphere in the way that I do it. Heather's going to talk about retrievals, which is a different strategy, but you could construct a similar flow chart. So you start with some initial guess for the temperature structure. you're going to assume this is a one-dimensional atmosphere I'm talking about here. That spherical potato, we're going to try to construct an average representation of its properties. So one dimension should be fine. I'm going to start with initial gas. That could be from a gray, simple gray or simple double gray approximation for the opacities and write out an analytic expression for the temperature structure almost. I'm going to assume hydrostatic, so that's going to provide me with from my temperature radius grid to get me pressure and density. Hydrostatic means I'm going to assume there's no flow up and down in the atmosphere. Everything's nice and stable. I'm going to assume everything is in equilibrium here, so including chemical equilibrium and local thermodynamic equilibrium. So only so the various abundances of the molecules and atoms and so forth are depending on the local temperature and pressure at each layer in my atmosphere. So you can lost my chalk. So imagine you're in a plane parallel case. I have different temperatures and pressures in each of my layer, and by assuming everything's in equilibrium, I can just take that temperature and pressure that I get from this step, plug it into a chemical equilibrium code, and get out the mixing ratios of everything for an assumed abundance, solar abundance, for example. I just call the occupation numbers that hold over from atoms and ions, the level populations, Boltzmann statistics, but also the energy levels populated by my molecules. Once I have that, I can then calculate my absorption, my opacities, my kappas, and my sigmas for scattering at each wavelength. And then I can solve the rate of transfer equation, here simple plane parallel, or I could do it spherically symmetric if the thing has low enough gravity where that might matter. And I do that at every wavelength. I loop over wavelengths, and I'm calculating the intensities and the moments, which are just integrals of the intensity weighted by cosine theta, the angle of the intensity vector. And then I compare that. Is energy conserved? And a quick way to do that is to integrate over all wavelengths. Do I get sigma T effective to the fourth? Because that's I'm making a model with a certain temperature and gravity here, a certain effective temperature and that gravity that goes in here. Do I get my sigma T effective to the fourth? My initial gas, of course, isn't going to be right. So the answer is going to be no. And so I'm going to apply temperature corrections at each step based on some algorithm. And I'm going to do the whole process again. I'm going to do I'll do this 10, 20 times until I satisfy this condition, for example, and a variety of others to my required precision. And then out pops my finished product, which is my model atmosphere, which will be my temperature, pressure, the run of abundances, the final spectrum, for example. I might post-process this to look like the observations, convolve it with instrument profile, change, reduce down to the sampling, do all the nasty things that instruments do to the real spectrum that came from the object to try to make that comparison. There's some nice reviews, Mark Marley and Ty Robinson in 2014 and Ivan Huberin that go into this in more detail. And these are sort of the basic ingredients. Just quickly, so the retrieval process would change this a little bit. Much of it would be the same. There'd be a wavelength loop. There'd be getting opacities. There's some flexibility that's thrown in. So the temperature structure is parameterized. And so I might just, maybe I would require hydrostatic. I don't have to. This step, the chemical equilibrium, I don't have to stick to that. I can just specify what my abundances are and then calculate my kappas, calculate the rate of transfer. I replace this energy conservation step with maybe a fancy pants statistics package that compares to some observation. And then I loop over that and find the best matching parameters. And then the out product is, again, a T and P and a spectrum, but one where the best fit parameterization of all the physics is in place. So there's some similarities there. I'm going to skip through that. Molecules. So this is a quick example showing you the relative importance of three main opacity sources: dust for two different gravities, low gravity in blue and high gravity in red, and molecules here. Most of this structure is water, and then collision-induced absorption. My entire spectrum will change based on the relative importance of these. If this is gone, my spectrum will be shaped mostly by the molecular absorption. If the dust is dominant, it's going to be very smoothly varying. If I have low gravity or high gravity, I'm going to change the spectrum as well. Quick example, kappa and. So here's a spectrum in black, and I'm showing a low gravity and high gravity, and I can estimate that. And what's happening here is I'm just changing the relative importance of the molecular absorption across the K band and the CIA, collision-induced absorption. I can make it flatter by making the gravity higher. I can make the moleculars more prominent by lowering the gravity. In the interest of time, I'm going to move through. I want to show this example. Coming back to my discovery, HD number 30 million year old something. Totally made up. These are actual real data from Brittany Miles' paper, UC Santa Cruz. I'm hiding the name of it. Here are the spectra and wavelengths. And this is a wide companion. It was very wide. I didn't have to use any fancy tricks. And so I get these observations. And so I'm going to run through my loop and calculate a model. And what's going to happen here? Yeah, calculate a model. I'm going to make an educated guess based on where it is in the color magnitude diagram. The temperature is 1200 Kelvin, and the gravity is low. This is consistent with the evolution predictions and consistent with my photometry fit. And so the products of the model are on the right. I've got the temperature structure in black. This is just as a guide where the condensation curves are of iron and silicon oxide grain. And so right around here and to the left are where you would expect those grains to form. And this is showing you the density of dust, not just these, but all of the ones that could condense. This is just a guide. And then the mixing ratio or mole fraction of CO and methane is plotted here. For reference, top of the atmosphere is here. Bottom, misspelling there, sorry. Bottom of the atmosphere is down here. And it's a technical word. I don't want to give you the details of that. Don't have time for that. So I plot the spectrum, and here it is. So I've got all this dust opacity, quite high. Look at that, 10 to the minus 4 relative to my molecules. That's quite high. So the red looks like this. So that's a terrible, and I've got synthetic photometry, integrated points in there for comparison. So that's a terrible comparison to my spectrum. The dust just makes it look like a black body. And all the wavelengths across here, you're seeing down to the same depth. So you're seeing down to the same temperature, and so it looks black body-ish. Okay, I didn't like that one, so I took the clouds out. I made them all transparent, and I get this one. Same, now the structure changes because I changed the opacity, so that iterative loop in my temperature corrections changes, so I get a different temperature structure. It's a little cooler now. A good chunk of this black dot's where the photosphere is, which is roughly where T equals the effective temperature. And so that's actually, this part is actually now below, there's a line across here which is the equal CO equal methane boundary. So high temperatures carbon is in CO, low temperatures carbon like in methane. And so that just changing the dust opacity, removing the dust opacity, lowered the temperature enough. So now the CO and methane are crossing. They didn't do that before. So that's a pretty dramatic change. But this really looks like crap, right? This is still not good. I already knew this from my color magnitude diagram. There was in between that cloud-free and that super dusty line. It was somewhere in between. I already knew that from the color magnitude diagram. So I wouldn't normally go to I would skip these first few steps, but I wanted to show you the dramatic effects that the opacities have on this. Now I'm going to say, okay, well, I didn't go through it, but there's a way to quench. So not all chemical equilibrium involves reactions. And so if you perturb the chemistry away from chemical equilibrium by, say, vertical mixing, you box up a bunch of gas deep in the atmosphere, ship it via FedEx up to the top of the atmosphere, and then open it. It will take some time for that gas to re-equilibrate with its neighboring gas. For some reactions, for most of the reactions, it's super fast. Poof, perfect, done, back to equilibrium. For some of them, involving CO and methane and N2 and ammonia, the reactions are slow and they scale with density and become longer than the age of the universe. And so if you can FedEx gas rich in CO and methane to the top part of the atmosphere and open it up, you will perturb it from equilibrium. And so that's what this, so this is called quenching or non-equilibrium chemistry. And so that crossing of the vertical mixing, my shipping time scales, my FedEx time scale, and then chemical time scale, where those cross, I'll quench and I'll keep the CO and methane constant. So that's what's done here. I still don't get a great match, but I'm looking better. Okay, I'm in the red. I'm almost done. I'll finish this example. So here I had strong methane absorption here, also here. And that looks more like I'm getting closer here, a weaker methane absorption. I've got some CO absorption because now I've got much more CO. Well, similar CO, but much less methane in this region. Still not great. So I'm gonna dial back my dust number density. I'm gonna say, okay, well, clouds are full of, this is dusty grains, and they're subjected to gravity. Gravity wants to pull them to the bottom, and they want to sink down here, and vertical mixing wants to keep them aloft. And so, yeah, I'm playing this juggling game, the competition between gravitational settling and vertical mixing. And so my clouds are actually going to look something like that. And that does wonders for the comparison. Now I'm closer to the colors that I had on my color magnitude diagram, and things are looking better. It's still not great. Still not great. I can do a little bit better. I can look over here in the L band, which has strong methane absorption. And I can see potentially some methane absorption here, maybe some there. I'm going to adjust the methane absorption and maybe try to find in a almost retrieval-like, but more cog by eye kind of sense in this case. I'm going to make a big improvement now by tweaking the methane abundance. I also cheated a little bit. I added 40 Kelvin and adjusted the surface gravity a smidge to make a better fit. And the real object will be named in Brittany Melville's paper and discussed in more detail. Quick gotcha. If you only had near-infrared data and did this exercise, you would get something that totally does not reproduce the L-band. If you only had L-band observations and did this exercise, you would not. So you have to be careful. Sometimes you need the whole wavelength range to get an accurate picture. All right, I'm going to skip to the last little. Just give me like 2 seconds. So here's that gallery of spectra again. You can do this analysis for a similar analysis, and empirically you can just look at this and go, okay, well, my hot objects like beta pick down to cool objects situated in an area, I can see a sequence. Methane is starting to appear. Here's HR879b, starting to show some methane absorption, and I get down here. Just to answer a quick question. So before, if you were to just go by the L and T sequence, where the T dwarfs and L dwarfs form around 1400 Kelvin, that line would be here. But we're already starting to see, so these objects over here don't show methane. They typically would have if you just went by effective temperature, or you would expect them to, but they don't. And so we are already starting to draw an important boundary that's demarcating the range where non-equilibrium chemistry is altering the CO and methane boundary in this diagram. All right, I have to stop. Those of you who joined me for lunch, I can finish the last 10 slides of my talk.
We have time for a question. Not Travis is going to be around, so.
Yep.
All right, well, thank you again.